session, which will be just chaired by Jakob Keiding and Pertti Sarala. So, please.
Yes, welcome back here to our conference on critical raw materials here on day 2. We'll continue with session 3 on new exploration techniques for CRMs, but first a practical notice. There was some inquiries yesterday about slides, and they will be provided through the EGT-TWINN project website. Most of them will be available later today, and also the first photos from yesterday are online under the web page, so please go in and check those and use them for social media, and also use the opportunity to take more photos during the day. Yeah, and then we'll go to the program. Oh yeah, also a last practical thing is that for those of you who are staying at the hotel and are checking out today, the checkout time is 12 o'clock, so please keep that in mind. And then we'll continue with today's first session here. That will be a keynote given by Vesa Nykanen from Geological Survey of Finland, talking about utilizing machine learning for mineral prospectivity mapping, a target generation of critical raw materials. Yes, the floor is yours.
Yeah, thank you very much. Good morning, everybody. Really good to be here in Tallinn, and thanks for the organizers for inviting me to give this talk. So the topic is how to use machine learning in mineral exploration, and more specifically using GIS and completing prospectivity mapping and targeting exercises. Most of these studies that I will show today have been funded by the European Union or Business Finland. So thanks for the funding agencies as well. Here's the outline of my talk. I'll start with a brief introduction, then a little bit about the background. What do I mean with mineral prospectivity mapping? Then I will describe some of the algorithms and methods of machine learning used, and then a couple of case studies as well at the end. And then some thoughts about the future directions and challenges we have, and conclusions. And hopefully we will have time for questions at the end. So what do I mean with mineral prospectivity mapping? So with this method, we are aiming to delineate areas that are favorable for some mineral deposit type or mineral system. And we want to save time and money and probably even environment in a way that we are taking most out of the data that we have. So these methods can be applied to any commodities, but I try to focus today how we have been doing this with critical raw materials, but basically any spatial phenomena you want to predict, you can use these methods, not only exploration. With machine learning, we can automate certain things and processes in mineral prospectivity mapping, and therefore try to enhance the method with these modern technologies. Mineral prospectivity mapping is typically based on a theory of ore deposits, or also it can be based on practical exploration expertise. But anyhow, you need to define the critical parameters of your ore deposit and then create map patterns, proxies to those parameters. So it starts from this theoretical part, mineral systems modeling, and then you select your data based on this, you pre-process, you create the proxies that define those parameters from your mineral system. And only after that, you start working on applying machine learning and other algorithms to create these mineral systems or mineral prospectivity models. And there are several different algorithms that you can use. and create this one single map that describes the potential of this mineral system or deposit type. And of course, at the end, you need to validate your models. There are several statistical methods you can apply, and of course, the final validation is go to the field and drill the targets. What I want to emphasize the importance of pre-processing of your data. Pre-processing the input data. Mineral prospectivity mapping is never so-called big data analysis where you analyze huge masses of your raw data. But you need to organize your data into meaningful map patterns that indicate the critical parameters of your mineral system that you want to model. And if you don't organize your data, you put garbage in and you will get garbage out. So this is probably one of the main takeaways of this talk. Organize your data. Don't use the raw data as it is, but you need to create these meaningful map patterns. We have two main approaches of mineral prospectivity mapping. First of all, empirical, and the second one is conceptual. In empirical methods, you need training sites to train your model. Known deposits are good examples of this, or it could be drilling targets or anything that indicates that you have this mineral deposit on that site. There are different methods like weights of evidence, artificial neural networks, random forests, and regression. We will come back to this later. The other method is conceptual. And here we know the controlling factors by our knowledge. We don't need training sites, but we can test different scenarios easily. Fuzzy logic overlay is one example of these and very widely used. And GIS is a perfect platform doing this all and applying these machine learning algorithms. Okay, what is machine learning? What do I mean with this? This is a field of study in artificial intelligence that is focusing on development of different algorithms and statistical models that enable computer systems to learn and improve from the data, from experience. And you don't necessarily need to program anything, just apply the algorithms. The algorithms can find the map patterns and make predictions based on this data that you have. So we identify patterns in the data, we learn from those patterns, and then we can make these predictions. There are a lot of different applications in engineering, including natural language processing, computer vision is one as well, robotics, data analytics, and now, as we talk today, mineral prospectivity mapping, where we use spatial data, which we analyze. We can divide machine learning methods into two main groups, supervised and unsupervised. The supervised machine learning methods, those can be used in MPM, mineral prospectivity mapping, to develop predictive models that identify areas with high mineral potential based on labeled data. Whereas unsupervised machine learning methods, you don't need this labeled data. And that's a huge advantage. So then let's go through a few examples of different algorithms and methods. I'm not going to go into details, deeply into details of these, just mentioning a few things. First of all, there are different kind of decision trees. Random forest is one of those methods which are good to classifying data into different categories. But you can also do regression tasks with these. The advantage with these methods is that you don't necessarily need a lot of labeled data to train your models. So that's a huge advantage as well. because later on, when we go on with in this list, support vector machine, logistic regression, artificial neural networks, these guys require a little bit more training. And both the previous ones and these, they require the positive labels, which are the known deposits, but you also need other set of training sites, which are the negative training sites that are telling you where we do not have the deposits. And that's a huge challenge. How to define these negative labels? These can be other deposit types, or this could be maybe, in some cases, random points, and you can generate them in different ways. But the problem there is that almost certainly you are creating some sort of a bias when you select your training sites. And then when we go even further on with this list, there are methods like boosting algorithms or deep learning algorithms, convolutional neural networks, example of that. With these methods, you need even more training than the previous methods to be able to complete the modeling exercise. So this is the difference here. So these require significant amounts of data and labels, and also computing power. So not that widely used as the previous methods because of these limitations, but there are a lot of examples coming how to apply this technology as well for exploration. Then the other group, unsupervised machine learning. Here we do not need labels to train your data. You don't need to have the known deposits. So this is very good in greenfields exploration areas where you don't necessarily have a lot of training. Different kind of cluster analysis, principal component analysis, which is very traditional method. And self-organizing maps, which is, well, not that new either, but it's widely used nowadays for this classification purpose, that these are mostly used. Because you can easily find the clusters in your data, but how do you define what is the meaningful in your case when you are studying or trying to find ore deposits? That's the challenge here. Okay, then at GTK we have been developing different kind of tools to apply these technologies. This is quite old toolbox we have. It was originally developed by the US Geological Survey and the Geological Survey of Canada already a couple of decades ago. Also, University of Campinas from Sao Paulo, Brazil, has been maintaining this toolbox for a while, but currently the maintenance is at GTK. And we've been using also Business Finland funding in these projects where we develop further this. And currently we have a project called Artificial Intelligence in Mineral Exploration, AMEX, where we are further developing these tools. The toolbox has, in the current version, quite traditional methods like weights of evidence, logistic regression, but also machine learning methods like boosting algorithms, random forest, support vector machine. In the future, in the current project, we are aiming to include even more machine learning and even deep learning, if possible. But this project is still going on, and the aim is to get all these tools done during the next year. Okay. This toolbox is quite peculiar. You don't need to install any software on your computer. This runs on a web browser. It's called npm Online. where you can build simple fuzzy logic models, fuzzy logic overlay models, using public geodata from northern Finland, and this is GTK data. You just run it on your web browser, and the address is over there. And current version covers only northern part of Finland, Lapland area, but in this ongoing AMEX project, we aim to update this toolbox so that you can run the models covering the entire country, and also include more deposit types. Currently, you can run orogenic gold, IOCG, and nickel copper deposit types, but then later on we will include more data sets and training sites so that you can also exercise something else. And we aim to include, in addition to fuzzy logic, a random forest model there. Third one is called GIS-SOM, so unsupervised method. This was originally developed in a EU-funded project called NEXT, and currently we are further developing this on ongoing EIT raw materials funded project, which is called DroneSOM. So this tool you can use to cluster and visualize your data. And you can download it from our GitHub site. I'm not sure if I mentioned, but the first tool here is also in GitHub, so you can just follow this link and download the toolbox. Then we also have a project funded by European Union from Horizon Europe. This project is called Exploration Information System, EIS. This is a pan-European consortium. We have 17 partners, 6 from EU countries and 2 partners outside of EU, 1 from Brazil and one from South Africa. This project is developing new geomodels, mineral systems models, and eventually even a mineral systems library, and a novel and fast and cost-effective spatial data analysis tools for mineral exploration. And now this one runs on top of OpenGIS, QGIS. So that's the difference if you compare it to the other tools that we have developed. Now we have changed into this OpenGIS platform. And the project website is over there, so you can find more information. And this EIS toolbox is based on idea of combining mineral systems modeling and MPM, mineral prospectivity modeling. So we define the mineral system parameters and then process the data for the MPM. And in the toolbox we have the tools for these different steps in this modeling exercise. Okay, and now let's have a look how we have applied these different methods over the past 15 years or so. The first one is our early study. This was published in Natural Resources Research 2008, and here we are applying artificial neural networks to combine the data. So we use data from geology, geophysics, and geochemistry. Unfortunately, the font is so small that you probably cannot see the labels there of those maps. But these are basically based on mineral systems model. So the parameters that describe the ore deposit, the important processes required to form the orogenic gold. Not a CRM, critical raw material, but a good example how to do this modeling. This method requires 2 sets of training sites. So we have the positive labels, which are the orogenic gold deposits, and then we have other deposit type, some other deposit type, I think it was industrial minerals, representing not deposit sites. And one feature with this model is that you can weight your training sites based on some criteria. In the first example here, the upper map, we did not use any weighting. So all the gold deposits were treated equal. So you can see a lot of high prospectivity areas, the red areas there, and Suuri Kuusikko, Kittilä gold mine in the middle is one of those. But a lot of new targets as well. But then the second one, we applied weighting, and based on the size of the deposit. And suddenly you can see that there's only maybe one red pixel in the map, which is Suuri Kuusikko, Kittilä deposit. But we do have the second highest class as well. So I think it's more realistic to look at the lower map with the weighting. Then second example comes from much newer paper, 2020, and again in natural resources research. Here the study area is Iberian Pyrite Belt, and deposit type is VMS. And here we are comparing 4 different machine learning algorithms: Brown Boost and Ada Boost as a group, logistic regression, support vector machine, and random forest. So widely used machine learning methods nowadays. We found that the performance of these different methods was quite similar, and especially the boosting algorithms were giving quite similar outputs, and they slightly outperformed logistic regression and support vector machine. This Ada Boost is user-friendly due to quite short training and prediction times. They gave high predictive accuracies, and I think it's a potential data-driven alternative for regional scale. But again, it depends so much on your data. We have also different kind of experiences using boosting methods. Sometimes they are kind of overtrained as well, so you need to be careful when using these. The next study is from Finland, target scale or camp scale. So this is this Rajapalot project area in northern Finland, northern Fennoscandian Silt in Finland. In this paper, prospectivity modeling was implemented using knowledge-driven and hybrid expert systems. So we combined 2 different approaches. And prospectivity analysis related system and model uncertainties were addressed using statistical and machine learning-based methods in this paper. Sorry about these really busy slides, a lot of stuff there. Prospectivity modeling results of this target scale are shown here in these 4 maps. The first one, A, is a prospectivity map from fuzzy inference system, and it was optimized using Monte Carlo simulations as well. B is a fuzzy inference system prospectivity map at 10% confidence level, and the C is at 90% confidence level. And the final combination of using this fuzzy inference system and neural network are in the last map. We have also indicated the known targets and new targets in the map, but probably the font is so small that you cannot really see them. Next example is again from the same camp scale study area, Rajapalot in Peräpohja belt. And now, instead of using these machine learning methods requiring training, we are using self-organizing maps first, and then applying artificial neural networks for targeting. So we create the clusters, and then we try to find which clusters are meaningful. So this is the way you can use these unsupervised clustering in MPM. You first create the clusters using this SOM method, and then you have a lot of clusters, and you need another method to tell you which ones are meaningful for exploration. So we demonstrate this application of machine learning, as I mentioned, using unsupervised SOM and K-means clustering as well, and together with this artificial neural networks. And in the final map, you can see over there on the right corner the combination map of these two methods. So we have created a lot of new targets for exploration. And to my knowledge, the mining company who was working with us is also, or has been testing these targets by drilling. Then the last case study that I will show today. This is something which is still going on. And here we are using this new toolbox that we are developing in this EU-funded project called Exploration Information System on QGIS platform. And we start by creating prospectivity model using critical system parameters as input. And here is one example of a really busy table that you can use. So you have the theoretical criteria here on the left, and then on the right is your output map, which you will then use for your modeling. So, for example, we try to find basalts, metabasalts from our geological map and use this information in the modeling, or certain parameters from your geophysics. This model was created for Iberian Pirate Belt, and we noticed that we need to modify it for Fennoscandia. It doesn't apply as such. So that's why this is still ongoing. We're currently adding more parameters and leaving out some. For example, the quartzite here might not work in our region in Fennoscandia. But for Pirate Belt, this was a good model. So now, in the version that I was using when we did this exercise, we had 4 machine learning methods: fuzzy logic, which is maybe not a good example of machine learning, but it can be used in machine learning, logistic regression, and random forest. We also had boosting, but the results were not very good, so I'm not showing them yet. I think that there's maybe something wrong with the code, so we are checking this. With the current version, we have implemented even more algorithms and tools. So if you want to run the tests yourself, you can nowadays, I think, include also artificial neural networks and probably deep learning as well. So we have been adding new algorithms there. So the modeling was based on the previous table. So those were the inputs that were mentioned there. And then we applied these different methods. And this ROC-AUC is one statistical measure that you can use to evaluate how well your model has performed. So the closer to 1 this value is, the better classification your model is giving when you use these validation sites. So from this we can say that random forest was the best one, and there is some difference. So this is for me quite interesting to see, and this is how we evaluate in the future when we compare these different methods. Okay, I think I've been moving quite fast, but let's go to the summary and key takeaways. There are a lot of different methods available for mineral prospectivity mapping, but definitely no silver bullet. You just cannot use one method, and my suggestion is to use different methods and compare the results. It's so easy to run these different models that you should always run different methods and then make comparison. But this data pre-processing or feature engineering is really important. Garbage in, garbage out. Maybe the most important takeaway message. The machine learning has really potential to discover new deposits and areas that have been overlooked previously. And we call this survival bias. Typically, our models or conclusions are based on success stories. But what about those that failed? We can also learn from those. So when we use these unsupervised methods that can learn from data, and I think there is a possibility that we start also being aware of the weak signals. Something which is in between from being non-deposit and a deposit. And then there is a possibility that we start finding the deep deposits as well. The machine learning methods in general have improved the accuracy and efficiency of MPM, especially the efficiency, but it seems that also the accuracy, based on the statistical tests, at least in some cases. So in that way, we can reduce the exploration costs and maybe even the environmental impacts. If you get more out of your data, you might not need to collect new data as much as previously. And then, of course, data quality, interpretability, and different biases involved, they can cause challenges how to use these methods. And then some recommendations for future research and development. One of the most important things to be developed definitely is how to transfer your mineral systems models into mineral prospectivity models, how to make this comparison on combination what we have been doing in this EIS project. Can we do it even better? And how to translate the critical parameters of mineral system into these proxies, these map patterns that mean geologically something, and describe the mineral system. And then it comes to the validation, how you define a meaningful model, what kind of tests you can use to show this, and how to measure this performance. There are different statistics that you can try to use. And this is really interesting field of research as well. And then a few references, just to remind you. Spatial data modeler can be downloaded from our GitHub site. Then there is a link to mineral prospectivity modeler online, MPM online, running at GTK website. One older project which we used to develop these tools, MPM, funded by Business Finland. Ongoing projects, exploration information system, DroneSOM, and the toolbox GIS-SOM, which is currently developed by this DroneSOM project. And also Business Finland funded project called AMEX. So here we have links to all these. And thank you very much. That's all.
Thank you very much, Vesa, for this nice overview of mineral prospectivity mapping and applying machine learning. I would like to start off by if you could briefly elaborate a little more on the challenges of using this methodology. I mean, you said data quality and accessibility of data is one of the key issues, but what about computer powering in terms of having access to enough computational power to do this kind of assessments, and also knowledge about training and so on? Could you?
Okay, thank you very much for this question. In general, I think that the data that we are using is very good quality. At least we have been used to have this good quality data. But then the major challenge is, as I mentioned, how to translate this data into these meaningful map patterns and how to create those proxies to those mineral system parameters. So it requires a lot of expertise on exploration. So you just cannot give the data into a data analytics guys who not necessarily have geological background. So you need to have a team of experts working with this. But when it comes to the computing power, the traditional methods, most of these do not require a lot because the data, you might think that there's a lot of data and it requires a lot of computing power. It's not. Yeah, I mean, we are dealing with typically a raster resolution of 50 meters. That's the high resolution data. So number of pixels in your maps is really not that much if you compare it to something else. So we can deal with that. But some of the algorithms, like the deep learning ones, they require a lot computing power. So, and training data as well.
What about, I mean, typically it's been applied, I mean, this kind of methodology to like organic gold and, I mean, commodities that has been mined for a long time and where we know the systems fairly well. But what about some of all these new commodities? We heard about lithium and pegmatites yesterday and so on. What is the prospect of using this method for those commodities?
Again, very good question. Yes, that's true. Mostly these methods in the scientific literature are so that these methods have been used for deposit types that are most common in exploration. But we also have currently running projects where we apply this for lithium pegmatites. And it just depends on the fact that you need to define the mineral system and create the proxies. And I'm sure that there are challenges because some of these have very weak signals in our geophysics or geochemistry. So how you find those weak signals and distinguish them from your background.
Well, some questions from the floor.
Samuel from Syntec. Thank you very much for a very good presentation. I just have some questions. I just want to know the models that you develop, how flexible or versatile are they? How is it possible to apply them at different locations? And then the second question too is that do you have a database? I'm not a geologist, I'm asking maybe it could be a stupid question, but do you have a database that gives you more information about the geological or the mineralogy of all of Europe? So that in case somebody wants to do machine learning, you have a database that you can go to get the correct data to be able to feed into your models.
Okay. Yeah, well, first of all, thank you very much. The methods, all of them are fairly flexible. So you can change parameters, you can run the models again, and you can iterate. So yeah, that's the nature of using these platforms that we have. So yeah, they are flexible. And when it comes to the databases, in Finland, we are in a quite nice position to have our spatial databases public. So it's easy to run these exercises in Finland, but in some other countries, it might be a different case.
Hey, what are the most useful input data sets for mineral prospectivity modeling?
I would say that airborne geophysics in Finland is pretty good because it covers the entire country and it's good quality and and there are a lot of parameters that you can translate in and use the geophysics. Your structures and so on, they come from the geophysics, so yep.
Thank you. Can I quote you back to the UK government, please? Thank you.
A question more up here from Torkel? You can get the microphone over there.
Okay.
You mentioned this about automatically recognize patterns in the data, and are you then talking about, let's say, predefined patterns or hidden patterns or unknown patterns?
Sorry, hidden?
I mean, you mentioned this about, algorithms that can automatically recognize patterns.
Patterns, yeah. Okay.
And are you talking about, let's say, predefined patterns or hidden unknown patterns?
Yeah, unknown patterns. So that's the idea of using, for example, self-organizing map. It finds from your multi-dimensional feature space, it finds those clusters, which I call patterns. So
Yes, this I agree on.
yeah.
But let's say typically also you do let's say feature selections before you input there.
Yes. So and then when you you're right. When you select the data, you are creating bias because you have selected. So these are not entirely data-driven in that sense, that always when you select the data and create the map patterns that I call meaningful map patterns or proxies, you're always creating a bias because if somebody else is doing it, this person might do it in a little bit different way. I'm not sure if I'm following your...
Yeah, I think you have a common understanding about this.
Yeah.
Okay. Another comment...
Totally.
Yeah, it was just, you mentioned that you're making use of magnetic total field, maybe corrected from resonance. I would say that it could be a little dangerous to do so. I would prefer to transform it so that you get rid of all these cycles, negative cycles, when you have the magnetic data. How you can easily do that.
Okay, thanks for this comment because, yeah, using all this data requires always experts to process your data, and it's teamwork, as I mentioned. So I'm not really expert on geophysics, so...
Yeah,
but yeah.
We can discuss it afterwards.
Yeah, thank you very much.
Thank you, Vesa, for the talk, and we'll have to move on.